it goes like this. There was a time when people believed that the Earth was stationary and the Sun revolved, and then Copernicus came along and said, no, the Sun is stationary and the Earth revolves. Now, they were both roughly adequate to the data. They both gave roughly equally good predictions, but Copernican theory was supposedly simpler than the Ptolemaic theory because it got rid of the equant. It had epicycles, but it got rid of the equant, so that made it simpler. The trouble is that it didn't fit well with the dynamics of the day, because the Ptolemaic theory of astronomy was consistent with, or fitted well with, Aristotelian dynamics, whereas there is no way that the Copernicans could explain how the Earth moves. And in fact, it needed another 100 years at Newton to explain that. So, in terms of coherence with other views, the Ptolemaic view was better than the Copernican view. So, one of the criteria spoke for Copernicus, one of the criteria spoke for Ptolemy. So these criteria are not guaranteed to end up on the same side. So what do you do when some criteria go one way and some criteria go another way? Well, you choose the theory that is sort of best on most of the criteria. Now that's vague, of course, and you can make it a bit more precise, but the basic idea is clear enough. And it can well be that an inconsistent theory is overall the best theory. It provides the best explanation of data, it uses the least number of ad hoc hypotheses, it meshes well with other theories. Okay, so it's inconsistent, so maybe that's a black mark against it, but overall it can still be the best theory. So you can think of inconsistency as a kind of defeasible criterion for rationality. But it's defeasible and it can be trumped by other things. Is that enough to answer your question?
It's okay. There is a package of things to see when you are concerning rationality.
Say again?
There's a package of things that you
Yes. Yes. So in some sense, rationality is cost-benefit analysis. And when you do the total cost-benefit analysis, it may well be that an inconsistent theory comes out best. And I think that's exactly the case with the theory of truth. But maybe we'll get to that in a minute. Okay. Any more questions before we move on?
Yeah, the criteria of rationality seems to be really close to science. I mean, empirical science.
Yes, yes.
Not close to math or logic. So that's pretty much different from what we learned here with physicians and other people. So one question that sometimes science has to answer when it comes with a new approach of phenomena is, why is it useful? What kind of phenomena your view can explain that other views can deal with?
Okay. Look, I think the account of rationality I've given you is quite general. It works whenever you are theorizing. Okay? And we theorize in science, we theorize in metaphysics, we theorize in ethics. In pure mathematics, I don't know that we theorize much. We prove theorems, okay? But let me not go into the philosophy of mathematics, because your main question is about logic, so let me talk about that. I think in logic we do theorize. Now, to understand why I say that, I'll have to talk a little bit about the distinction between a pure logic and an applied logic. So let me explain the distinction first not with respect to logic, but with respect to geometry. Okay? So we now know that there are many pure geometries. Euclidean geometry, hyperbolic geometry, elliptical geometry, geometries of non-constant curvature, and so on. And as pure mathematical systems, they are all equally good. There's no sense in which there's a rivalry between them. And we prove theorems about each, and that's perfectly fine. But of course, geometries can have applications. And geometry has what you might call a canonical application, because this is the application that the original geometry, Euclidean geometry, was meant to have, namely, to give a theory of the way that space and time behaved. Now, when you apply Euclidean geometry to space and time, not just as a piece of pure mathematics, but as an application, what you are actually providing is a theory of the nature of the behaviour of space and time. And we now know that the theory that Euclidean geometry gives us is wrong, at least post-special relativity or general relativity. So we now think that the correct theory of space and time is what you get when you apply a different geometry. But of course we discovered that with science. But we were theorising when we applied geometry in this way. So all of that is relatively uncontentious, that's clear. But if you think about it, you will see that exactly the same is true in logic. Okay, so there are many pure logics. There's classical logic, intuitionist logic, relevant logic, power-consistent logics, and just like geometries, as pieces of pure mathematics, they are all equally good. We prove theorems about all of them, we discover their abstract structure, fine. But of course, logics have applications. In fact, they have more than one application. So you can use a logic to simplify electronic circuits, to test for grammaticality, and so on and so forth. And different logics are correct for different applications. But just like geometry has a canonical application, so does logic. The canonical application of logic is to give an account of the correct norms of reasoning. Right? So if I say there are at least 7 people in this room, so there are at least 2 people in this room, that's a good piece of reasoning. Right? If I say there are at least 7 people in this room, so there are 143 people in this room, that's a terrible piece of reasoning. So there's good reasoning and there's bad reasoning. And when you take a pure logic and you give it its canonical application to reasoning, then that gives you a theory about what good reasoning is. So, suppose we're reasoning in mathematics, and I established that it's not the case, there's an infinitude of prime numbers, so therefore there's an infinitude of prime numbers. Is that a good piece of reasoning? Well, if classical logic is right, yes. If intuitionistic logic is right, no. So both those pure logics, when they're given their canonical application, give you different theories about what good reasoning is. So this is why I say that in logic we do theorise. So we try to choose the pure logic which, when applied to reasoning, gives us the best theory. Okay? So I do think that in logic we theorise. Of course, when we do pure logic, we just prove theorems, and that's not really that's not theorising in this sense. But when we apply logic, we are theorising.
So you're not just holding on belief and saying, well, I just believe in that, and that's a thing that I hold. You're trying to see what the world tells you, like what the phenomena tells you, what reason tells you. Is you're trying to, is that it? You're trying to see how things really are, not holding on a perception.
Sure. So there's this phenomenon of reasoning, which we all do. And there are norms for good reasoning and norms for good reasoning, which sometimes we follow, sometimes we don't, unfortunately. But we want a theory of what those norms are and why. And that's what an applied logic does for you. And logic has changed over 2,500 years in the West. Our theories have changed. So the theories of Aristotle are not the same as the theories of the great medieval logicians. They're not the same as the Port Royal logicians. They're not the same as Frege. And they're not the same as Brouwer. So, theories have changed, and logicians have argued about what the right theory is.
In these things, I think you don't need to find contradictions in the world in order to defend dialetheism. Even if there are no contradictions in the world, you can still defend dialetheism.
How do you do that?
So by constructing this kind of mathematical relation, evaluation as a mathematical
Oh, I
relation.
see.
So you don't need to see how the world is in order to say that there are propositions which are true and false.
Well,
It can work at the abstract level.
yeah, well, okay, look, tell me if I'm wrong, but I think by world, you mean the physical world.
Yeah, physical world. Yeah.
Okay, point taken, yes. And, it could be that the physical world is consistent and the abstract world is inconsistent. Now, I happen to think that's not the case, but that could be the case. In which case, there will be no contradictions in what you're calling the world. The contradictions are in the structure of abstract objects.
Yeah.
And that's not an implausible view. Yeah.
But in any
So
case,
I think we have to continue, otherwise you will not be able to explain these topics 3
Well,
and 4.
I don't really care if we don't get to that. I mean, I'm